Hello, my name is Robert Timothy Niven, and I am a student at Cape Fear Community College. Today I have a project demonstrating the power of MATLab and how to use it in certain scenarios regarding Physics 1 and 2. If we go now to A, our topic for today is rotational kinematics and solving for angular acceleration and force. Our concept and relevant formulas are from one of the physics textbooks I was given, and it demonstrates that the different rotational kinematic formulas, as well as the comparisons between normal kinematics, because kinematics are equations based on motion. So rotational kinematics are formulas based on rotational motion around a fixed object, like if you were to spin a CD on a pencil or a drill head or a gear, anything of that sort. So for our solved example from the text, most of this is just a CD player, right? So if you put a CD into a CD player, it rotates around that fixed axis to play it. And initially, they'll solve for the angular speed, and then they'll end up getting 2.1 times 10 to the second revolutions per minute. And then they will solve for how many revolutions, which is the angle theta. And then finally, they'll solve for the angular acceleration, which would be negative 7.6 times 10 to the negative 3 radians per second squared. So our first solved problem, aka the tutorial problem, involves a 0.75 meter door weighing 1 kilo, and it needs the ability to rotate at least 270 degrees. A piston is placed a centimeter from the right side of the door. How much force minimum will the piston have to enact to rotate the door 270 degrees in under 2 seconds? So initially we're given the four formulas, the angular acceleration, angular acceleration, angular acceleration, angular acceleration. There are actually 5, but only 4 of them involve angular acceleration. So due to the givens, we're going to choose this formula right here. And then if we plug all of our variables in it after converting the 270 degrees to radians, because if you do not, it will not work properly, it'll give you your angular acceleration of 4.7124 revolutions per minute squared. And then if we go into part B, to find regular acceleration, we have to do angular acceleration times the radius. And the radius here would be 0.75 meters. So then if you multiply those together, you get the normal acceleration, which is 3.5343 meters per second squared. And force is mass times acceleration. The door weighs 1 kilogram, and you multiply those two numbers together to get 3.543 newtons. So for our MATLAB code, all of this right here is just to give you an explanation of what all the variables stand for. The one real thing that stands out is that theta has to equal x instead of theta, because it's really complicated to get the letter theta in there. All of this code right here is just trying to fill in all of these variables that were initialized before. Once you type in the summon command, it'll pull all of these up, and then you'll fill in. So say starting velocity 0 radians, 3 pi over 2, all of that, etc. And then this code right here is where it gets a little complicated. Pretty much all these if and ends are due to this input right here. So you'll have a discarded variable, and all the kinematic equations are missing one variable. So that's why the fifth equation, it doesn't have angular acceleration. So if we're missing velocity, then it'll go to if w equals v, and then it'll solve it out using the equation that doesn't have velocity, and then so on and so forth. This way, you can more vary how you use it. And so you'll save it as rotational kinematics, and then call it by typing rotational kinematics. It'll pop up all of these. You plug in your variables, 1, 2, 1, 3 times pi over 2. For this one right here, I just put 1 due to the fact that sometimes for starting velocity you can get 0 as well, but final velocity we don't have, you would still plug in 0. And then our discarded variable would be velocity, and then it gives you these right here. So tutorial problem 2 is pretty much identical to tutorial problem 1. The only difference is we are able to use a different kinematic equation. So for that as well, we come down to the code here. Our discarded variable would be x, aka theta. And then we go down to tutorial problem 3. Tutorial problem 3 is pretty much the exact same as tutorial problem 2. So it solves for which equation we need, same equation as before, and then it solves for the force, which you'll end up getting right here and right here. So then if you plug it in, it'll give you the exact same numbers. Now, when it gets to tutorial problem 4, I wanted to show that even if you don't want to find the force, you can still find the angular acceleration. So if we're only given the time, the angular speed, and the initial angular speed, as well as the... Okay, no, those are the only variables we're given. This is just conversions right here to revolutions per minute, which is what we use in this code. So if we come down here for analytical solution, you're just going to use this formula, and it'll come out as 38 revolutions per minute second squared. And so that's another reason why the put 0 for unknowns, if understood, answer 1, because now the mass is not there and the radius of the circle or lever arm isn't. So it'll pump out the answer as the force is 0 and still give you your angular acceleration. Tutorial problem 5 is very similar to tutorial problem 4, just finding angular acceleration. It uses a different kinematic equation, a more complicated one, but still, nonetheless, you're able to solve it out and get 14.51. Same thing with the code. Plug everything in, and then you'll get 14.51. So my concluding statement for this project is, the use of this project was actually to help me solve a real-world problem involving opening a chicken coop door automatically. This code allows me to figure out how much piston force needs to be exerted on the door to make it complete a 3/4 of a revolution in a certain time frame. I am able to adjust whatever variables I need and to further help me get an answer. This equation could be applied to many other problems, even as a checking solution for how many revolutions a motor, wheel, and hinge should make. Overall, this equation setup is applicable for real-world situations, and that's what makes it so much more useful. Not to mention how powerful this MATLAB code is. The MATLAB code makes it so that you could do this in under like 5 seconds, really. You just plug in all your variables and boom, you have an answer. Versus doing it in real life, you'd have to solve for the kinematic equations, figure out which one. It would take 5 minutes. So that is why this code is also very useful. Thank you.